You're listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI, and much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast. This week's podcast is based off our webinar about inductors, and it is divided out into two sections. Now, this is not the same webinar from George Slama. This one is a bit more advanced. Join us as we head down to Mexico and hear from Maximiliano Padilla, Technical Chat Navigator with Wurth Elektronik Online. Now, during our time, we will define inductance. We'll also cover the Q factor and learn about different types of inductors and what the effects are of wire type and core material for this type of component. Enjoy today's Wurth Elektronik What's Up podcast, Power Up with Power Inductors.
Let's start by defining the inductor. This is a passive electrical component that stores energy in a magnetic field when an electric current flows through it. The inductance limits the change in current once a voltage is applied. 1 Henry is a measure of inductance of a closed circuit that produces 1 volt when the current varies 1 ampere per second. And also, 1 Henry is equal to 1 Weber per ampere. An inductor basically consists of a coil conducting material, which typically is insulated copper wire wrapped around a ferromagnetic core. There are also different types of inductors based on this core. Some examples of these types are shielded, unshielded, and air core. As I mentioned before, the inductance is measured in henries, and it can be calculated with the following formula. Once we have parameters such as the permeability of free space, mu sub 0, the relative permeability to air, mu sub r, the effective cross-sectional area, A sub e, the number of turns squared, and the effective magnetic path length, L sub e. We have to be very careful when we calculate this inductance due to the fact that inductors are temperature and frequency sensitive. This means that the inductance value is valid only at a given frequency and temperature. If one of these factors is changed, the inductance changes as well. Always keep this in mind. Now, let's talk about the Q factor, which is the quality factor on an inductor. This is the ratio of its inductive reactance to its AC resistance at a given frequency. In other words, it is a ratio between the stored energy, which is the reactance, X sub L, and the losses, in this case, R. The higher the Q factor on an inductor means the closer that it approaches the behavior of an ideal inductor. This translates to the inductor's efficiency. Calculation of the reactance can be done by multiplying 2 times pi times the frequency in hertz times the inductance value in henries. All the loss components can be combined into a loss resistance, in this case R. This is primarily responsible for defining the quality of the inductor. If the inductor is used at higher frequencies, the losses increase rapidly. Unfortunately, mathematical determination of this loss resistance is not possible. Therefore, inductors are usually measured over the entire frequency range with an impedance analyzer. which provides the individual components such as reactance, resistance, and impedance, of course at a given frequency. When we have filtering applications, a lower Q factor would be needed, whereas when we need a storage inductor, a higher Q factor would be required. There are two main factors that define an inductor's behavior. On the left side of the diagram, we have the core, which controls the saturation current of the inductor, and it can be made from hard ferrites such as iron powder and other alloys. And also there are soft ferrites. Some examples would be manganese zinc and nickel zinc ferrites. We will review the main differences between each of them. The other main factors that contributes to the inductor's behavior would be the wire, as shown on the right side of the diagram. This defines the rated current value that the inductor has. And this wire can be round or flat, depending on each application. We will also review each of them to know their main characteristics. First of all, let's take a look at the core and its behavior. You can see on the screen the commonly known hysteresis curve, also known as the VH curve. It shows the magnetic flux density as a function of an imposed magnetic field. This profile is dependent on the core material of each inductor. According to the value of the coercive field strength, we have two main categories, which are the soft ferrites, which would be the upper curve, and the hard ferrites on the lower curve. The coercivity is the resistance of a magnetic material to changes in magnetization, equivalent to the field intensity necessary to demagnetize the fully magnetized material. Soft magnetic materials are mainly used in inductive components, whereas hard magnetic materials are mainly used as permanent magnets and with electromagnets. As shown in the hysteresis curve, even if the field strength H has returned to zero, magnetic flux B is still present. B sub R is what we call it. However, if we want to reset the flux density to zero, a certain negative field strength has to be applied, which is called the coercive field strength, H sub C. With this in mind, let's analyze soft ferrites, which have low coercivity, meaning that they are easy to demagnetize. An example of this soft ferrite would be manganese zinc and nickel zinc. You can see the behavior on this type of cores on the following animation. It visually shows how easy it is to demagnetize this material. On the other hand, hard ferrites have high coercivity, which means that they are difficult to demagnetize. This is a characteristic of iron powder cores. And here also the animation shows the difference between these two, and you can see the comparison between both of the hysteresis curves. You would need a stronger magnetic field in order to magnetize or demagnetize this type of cores. So how does this translate to the saturation current? As previously mentioned, the core material is directly related to the saturation current on an inductor. This is the current at which the initial inductance value has dropped by a percentage specified in datasheet. This percentage can range from 10% to 40% and must be carefully checked as the value varies among different components and manufacturers. The following graph shows both materials with their inductance percentage drop and how this is affected by the current flowing through them. Once the saturation current is surpassed, you can see the main differences between them. The red line shows the subferrites. We call this the saturation knee or hard saturation. Since this material is easy to demagnetize as previously shown, the inductance value drops almost immediately after the saturation current is surpassed. And the black line shows the hard ferrites. As you can see, the behavior is quite the opposite. We call this subsaturation, due to the fact that the inductance does drop once the saturation current is surpassed. However, due to the high coercivity, this inductance drop is very slow or gentle. Now, let's talk about permeability versus frequency. Permeability can be described as a magnetic conducting or penetrating property, analogous to electric resistance. The relative permeability of the material is not constant, but nonlinear. This behavior is essentially dependent on a couple of factors, such as the magnetic field strength, which is dependent on operating conditions, the frequency, the temperature, and the material. Core materials can only be used effectively in the construction of inductors within a limited frequency range, as a result of the frequency-dependent loss components. Core losses rise sharply above a typical frequency limit. The following graph demonstrates the relationship and the limits of these core materials. It plots the inductive parts of impedance, X of L, and their frequency dependence for 3 different core materials. You can see the comparison between iron powder in the black line, manganese zinc in red, and nickel zinc in green. This test was made at room temperature levels, in this case 25 degrees Celsius. It is worth noting that iron powder materials may be used as pure inductance up approximately 400 kilohertz. The loss component dominates subsequently up to approximately 10 megahertz. This type of core would be ineffective in the frequency range above roughly 20 megahertz. Now, manganese zinc cores are inductive up to frequencies around 20 and 30 megahertz. Losses are usually rising above 10 megahertz, and the core material is no longer effective in the frequency range above 80 megahertz. And finally, nickel zinc cores are inductive up to frequencies around 60 megahertz. If we keep increasing this value, the core material is no longer effective above approximately 1 gigahertz and beyond. So this graph basically demonstrates why nickel zinc ferrites are predominant in the EMC field. The core material can perform an effective filter function in the frequency range of the greatest interest. We can also point out the typical initial permeability values of these cores at this specific test condition. Iron powder cores have a permeability between 50 and 150. Manganese zinc cores are between 300 and around 20,000. And nickel zinc cores would be between 40 and 1500. With that said, let's analyze how the permeability behaves when the core experiences a temperature change. The following graph shows the initial permeability as a function of temperature. This test was made at a frequency of 10 kilohertz. The initial permeability values of each core remain as previously stated. Now, Coils having ferrite core materials show a variable inductive behavior with change in the ambient temperature. There are two important concepts to take into consideration. On one hand, the maximum operating temperature range, and on the other hand, the current temperature. It is highly recommended that the temperature of the component does not exceed this maximum operating temperature under worst case conditions. This range is dependent on core material chemical formula. And while the current temperature is the point where the ferrite material loses all its permeability. This is why the inductance drops to zero, as pointed out by the arrow on the graph. However, this condition is not permanent. Once the ferrite cools down, the previous permeability is restored. Generally, the higher the initial permeability, the lower the current temperature. And typically, permeability presents a peak right before the ferrite reaches its current temperature.
This podcast was taken from a Wurth Elektronik webinar, and next week we finish with Max returning to discuss the construction of an inductor, specifics and differences in the wires, and the skin effect. To view the materials and replay the webinar on demand, click the link attached in this podcast. As mentioned before, our presenter Max is a technical chat navigator at Wurth Elektronik Online. You can chat directly with Max and the team by clicking the chat icon at www.we-online.com. You're listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists. We're going to shine a light on some interesting topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast.